Welcome everyone. Thanks for joining here. I have the opportunity here to promote a little bit our latest toolbox. Latest in the sense that it has just been published, and because it has just been published, I believe it's the right moment to share it with all of you. So the idea of this tutorial is, first I will go a little bit through a small presentation that will just give you the general overview of the main functions of the toolbox, and then afterwards we want to give some demonstrations. So I will open MATLAB and the toolbox so you can see that hopefully everything works smoothly. So let's quickly go through it. So we had just published this paper together with Iranian colleagues, and it came out last month or so. So that made that it's now the right moment to release it, because so in this paper you can read everything what I will be talking now about, and we also now in the demonstration case I will make use of data that has been published there. Unfortunately, I don't hear anything from my Iranian colleagues anymore because of the the strikes that are ongoing there. So with this also I hope to support our colleagues in Iran for their freedom. Yes, so the toolbox is part of the ARTMO ecosystem. Today we will just have a look at the classification toolbox, but there are many more toolboxes, and in fact lots of these classification toolbox come from older toolboxes, especially from the machine learning for regression toolbox. Most of the algorithms presented in this classification toolbox are actually coming from originally from the regression applications. So in order to access the ARTMO toolboxes, you need to go to the ARTMO website, you need to register, and then once registered, that brings you to the download page where you can download all these toolboxes in a modular way. So you need to download the basic ARTMO, and then you can download additional tools and toolboxes or whatever you like. However, I must say about the machine learning classification toolbox for today, even yesterday we found a small bug. And in case of when there are bugs, we rather recommend you to request for the HIT version that's in GitLab. And this is just by sending me an email, and I will add you to the list. And in this way, you have always access to the latest version. So for the classification toolbox, that will be then the version where this small bug was corrected. So only there that's the latest and the right software. Okay, so there will be two toolboxes, in fact, that I want to show you. First is this smaller tool, what we call the LabelMeClass, and that tool is developed to collect your labeled data, because at the end, the toolbox is a supervised classification toolbox, meaning that it needs labeled data for the classification. So the labeled data is just that you as a user define what are the land cover classes. Can be sea, land, water, vegetation, and so on, right? So that need to be labeled. It can be either coming from what have you collected in the field with the GPS, or you can manually collect it, for instance, with this LabelMeClass tool. And once you have your data collected, that is then used as input for the classification toolbox itself. We call it the machine learning classification algorithms toolbox. And why algorithms? Because I believe we are most state-of-the-art. We collected over 22 different machine learning algorithms. And within the toolbox, it's very user-friendly. You can just select all of them or whatever you like, and it will then evaluate them one by one. So a few words about this LabelMeClass tool. Later we will try, but basically you can load an image, and based on that image you can start selecting your own classes. So based on visual interpretation, sometimes that's very easy. When it's water or land, you can directly see that on the image. But also you have the option to load, based on GPS coordinates, a text file with labeled data that you have collected in the field. It will then identify if it covers within your image. And then based on that, we will select those labels. At the end, what is being collected is a file with labels on one hand and spectra on the other hand. And that's what's needed for the classification toolbox. So the data that is being collected actually looks a little bit like this, what you see in the bottom. And that will be the start or the input for the classification toolbox. Sorry, is there a question? I heard something. If not, I just continue. And so the label data, basically, most important are the labels, right? And label data is just per class, you give it a number. So the ones for land, the two for sea, and so on. Within the LabelMeClass tool, also additional information is being provided, such as the coordinates according to the coordinate system of your image, or the indices, also the location of the pixel numbers for each of these selected pixels. So that would be the input that will go into this kind of window. And basically, all what you have to do is you load your text file, and you have to tell which line consists of the labeled data. You can give it a title. Also, in this case, these were data that was collected over here, the Valencia region. So I call it Valencia, VLC. And then afterwards, also, you can give each of these class a name, so building, park, industrial buildings, and so on, and you can give it a color. And these then will be the colors that eventually will be shown in your final map. So here you define your colors, and you also can decide to remove some samples, or maybe you want to convert because your image is in other units. Your training data. So these are also some small options you can plot also, so you can see your spectra. In any case, once you are satisfied with it, you click on the bottom right on import. Once then that step is done, it moves to the most important step, so which is the settings. In the settings, you can have access to all the algorithms. So there are over 22 classifiers. We have organized them according to parametric classifiers, decision trees, error correcting output codes, ensemble learners, neural networks, Gaussian processes. Now, in this tutorial, we are not going too much into the detail of these classifiers. I think most of you are familiar with it, and also there exist loads of papers or Wikipedia pages about all these classifiers. In any case, I will give a few examples of these algorithms. So also in settings, you can add, if you wish, some noise, because sometimes your data that is being collected is more or is less noisy than your image, and maybe you want to add noise to improve. And you can also define how much of your data is being used for training and how much of your data is used then for testing or validation. Those are the basic steps. Later we will see there are a few more, let's say, more advanced steps. For instance, you can make use of cross-validation, sampling instead of simple training, testing, splitting. We have some band tools also that maybe in case of you have hyperspectral data, you rather want to first apply dimensionality reduction, such as a PCA, before actually applying the algorithms to the spectral data. Later we will go through it. So for now, I want to show you just some examples. Starting with the most simplest one, the parametric classifiers. The most known is the discriminant analysis, or also known as the maximum likelihood. Well, we all know this, and it has its advantages and disadvantages. But probably more of interest, and you don't need to read this all, it comes from the paper, are the non-parametric classifiers, or the machine learning algorithms. And here we can see, so we have decision trees and neural networks and ensemble learners and so on. But I think the key message is to realize that nowadays, for instance, a neural network or decision tree, it's not just one algorithm, but within this family of algorithms, you have all kinds of options on how to, well, different designs or different optimization options. So making that, it's not that we offer just one decision tree or neural network, but we offer multiple of them. And within each of them, you can still change several options and so the way that it tunes or optimizes. Here are some examples of these non-parametric classifiers. So the most known ones are the support vector machines, neural networks, and decision trees. Again, each of them with their advantages and disadvantages. Often the disadvantages of these kind of algorithms is that they are perceived as complex because they need maybe some knowledge what's actually going on, or some tuning of hyperparameters. But here I want to say that with the toolbox that we offer, the user does not have to take care of it. So we have it already optimized, the settings in what we believe works best. Of course, the user can change it. But the message is that actually you can just simply use these algorithms just like any other, such as the maximum likelihood. You don't need to do any additional tuning yourself also. You can do so, but also in the default settings, they are pretty well optimized. Finally, further, once you run these algorithms, an overview table will appear first with the most important, the overall accuracy. But also some other options are provided, such as well, the kappa index, the time that is needed for training and testing, so the total time of processing, or the training time alone, or the testing time alone. And it's important to realize that these algorithms or these, well, trained models, so it shows that for the validation data, and you show them according to a statistics, in this case, according to the overall accuracy. So basically, the very first one is the best performing algorithm and so on. But you can change these statistics, and you can also show them according to the kappa or the training time. And so you can actually query yourself the performances depending on your own requirements. Yeah, I don't need to go through the definition of overall accuracy. I guess everybody is familiar with it. So it shows the overall performance of the classifiers expressed in percentage. Apart from that, we can go into the results of each of these models and see how they perform for the different classes. And that would be the next. And now okay, yes, yes, okay, so one of them is the confusion matrix, so that it provides. So this is then for the, well, in this case, random forest, and it shows so how many of the samples were correctly assigned. So that's the diagonal line, and which of the samples are wrongly assigned to other classes. So you have the overall overview, and then also per class you have some statistics. So how about the percentage of correct and wrongly assigned of each of the classes. So that's the confusion matrix. And maybe the most interesting one are the statistics per class. So still the same model. We offer the most widely used statistics, so which is precision. Well, precision is a proportion of positive values that were correctly identified. Sensitivity, which is a proportion of actual positive cases that are correctly identified. Specificity, which is a proportion of actual negative cases that are correctly identified. And I think nowadays what is most commonly used is the F1 score. And the F1 score is this weighted average of precision and recall. So that gives a little bit an overview of each of these statistics. And so that gives you the information for each class, how well that class is identified. We applied that to this Iranian database, and so we had 4 classes. These were plant types, so just vegetation, different plant communities that we tried to classify. With the data was Sentinel-2, and we added also some additional bands based on PCA. And then we gave an overview, and here I just show you the 6 best algorithms. In this case, the Gaussian processes classifier was evaluated as best performing, and I was really happily surprised because it's a not well-known classifier, yet in this case at least it's able to outperform random forest and other decision trees and neural networks. And this classifier is specifically of interest, and I'm a big fan of these Gaussian processes, because apart from just classification, it also provides all kind of additional information. On one hand, as you can see in the top right, it gives you information of the ranking of the relevance of the ranking of the included bands for each class. And that polar plot shows, so for these 4 classes, what were the key bands for identifying each of these classes. So we can see there is some PCAs and then some Sentinel-2 bands. On the other hand, apart from the mapping, it also provides uncertainty, and that's also very relevant, because with this uncertainty, we can see where the classifier is doing a great job and where it's doing a poor job. And a poor job typically means that where there is a lack of training data. So it means that, okay, yeah, I do a classification here, but I'm not so sure, because the spectra that I encounter here actually differs from what has been presented during training data. And why is this of relevance? Because actually it tells you where you can go back into the field to collect additional samples so that you can be more certain about those areas that you classified correctly. Another thing, and we will not cover that today, but in the latest version, so on HIT, we also offer a so-called band ranking tool. So since this Gaussian processes has these band ranking properties, and this is more for hyperspectral data, but it does analysis starting from all the bands that you have, and each time removes the least important band. So it classifies again, removes least important band, classifies again, until finally, well, one band is left. And in this way, so you have an overview of the performances from all bands to one band, because very often actually the best classifier or best regression is not with all bands, but is with a limited number, but the right one, correctly selected bands. So you can see for finding your optimal number of bands on the one hand, and on the other hand, you have the information what are these bands. So you can see, is there any physical meaning towards these bands related to your classes? We've never explored it or published it, so if people would be interested in exploring this, I think it's worth a paper. Please just contact us and we would be happy to explain or to show you how it works. Yeah, here are also some examples of the other classifiers. And why I want to show this, because even though the validation actually was quite close to each other, the overall accuracy will vary between 90% and 80%. Yet when you apply the classification, you can see there are clearly differences in the maps, making that you should not always only just trust the validation, but also always have a look if the maps actually make sense. And here again, I think uncertainties help a lot to be more confident about the quality of the map. And here, finally, this is an example of Sentinel-2 over the Valencia region where I live. So we see the sea on the right, we see the lake, Albufera Lake, the rice fields where the paella comes from around it. We see the city, there is some big park in between the city, and then we see the well, agricultural fields and natural land around the city. So this brings me to close the presentation. We present this LabelMeClass and MLCA toolbox. We believe that from all the algorithms, particularly these Gaussian processes is of interest because of the band tracking property and provision of uncertainty estimates. So you can have access to it, maybe best in HIT, so you have the latest version. And right, I didn't show, but apart from this LabelMeClass, we also have a similar tool now also just released for regression. It's called LabelMe, and there instead of that you give labels, you can give continuous values to pixels that you select. So or if you have in the field with your GPS, you collected some continuous data, LAI, chlorophyll, whatever, you can then load in LabelMe directly that to an image, and it extracts the spectral data. So you have all the data directly prepared for your regression analysis. Good. If I have time, let's go to actually the demo case. So I will close the presentation and I go to MATLAB. I have ARTMO already open, but just for people to know how to, I don't know if okay, this lets me. If you see my screen, right? I hope so. So basically, you just have to type in within MATLAB ARTMO, and then that toolbox, this guy here, will appear. Let me make it a little bit wide so you can better follow what's going on. And let's go now to the classification toolbox. So it's part of the ARTMO. Here we have classification. We have the supervised machine learning classification toolbox. We have this LabelMeClass, and what is still under development, so probably that's for next year to show, is the unsupervised toolbox. For now, let's start with the LabelMeClass tool. Let's open it, and let's first open a simple image to manually select some labeled data. And here I will open this Valencia. It's an NVR and Sentinel-2 subset, and it will appear on the left panel. I can change the colors. Let me show it as an RGB. Okay, and So basically, okay, this is our image, and imagine that we want to classify it in a very simple way. So how the most easiest way is, so we just select manually some pixel of our class. So we click this button, it automatically suggests a number, and we just give it a name. So let's see, this is C. And all you do is just you click where you're sure that this is C. Well, this is the easiest class. And finally, you click on Enter, and by clicking on Enter, it selects the pixels and shows the spectra. So that would be one class, and now we continue. We have number 2, and let's here, maybe let's try to classify the lake. So lake, and the lake is here. So let's select a few. It looks more green because it loads of sediments and algae. Again, I click on OK. And now the spectra of the lake will appear. And okay, so far so good. So let's select one more class. And maybe now let's say city. And let's, of course, you can also zoom in. I think you should have done that before because now it's deactivated. That would make it a bit easier, but now let's just do it fast. And I have some city pixels selected. And right. So now I have 3 classes, but imagine that I'm not too happy with these classes. So you can decide to delete any of these classes. So you just give the number 1, 2, 3 in this case, I will not do. Or you delete the last group that you just created. Or you can delete, if you see that one spectra is not correct, for instance, you are supposed to search for water labels and you see it's a vegetation spectrum, you can click on delete line and then you can select manually one of them and click on enter, and ideally that should be removed. Exactly. So this is the way how to collect spectral data. And finally, we can edit the class names if we want. In this case, I'm happy, C, Lake City, okay. Or then finally, we can export the spectra to a file. And let me just search, yes, this Valencia file, and you give it a name. So I say 3 classes. Let's quickly see what's inside then in these files. Okay, so let's open the Valencia folder. And we can see that 2 files, text files were created. On one hand is a file with the data. And on the other hand is a file with the metadata that explains how the data is organized. And we can see that the first column from line 6 to the end is wavelength. The second column is the longitude in UTM, then the latitude in UTM, then the longitude as pixel value, latitude as pixel value. And finally, line number 5 is what matters. So these are the classes. And we have class C, Lake City, 10, 8, 7 pixels. And then underneath, we have the spectra. So if you have a look at it, so this is the labeled line. These are the wavelengths. In this case, apparently the image did not have wavelengths within the NV header file. So it just say 1, 2, 3, 4, 5 until 10. And underneath you see the spectral information for these classes. So this is the file actually that is needed now for the classification toolbox, right? So let me close this, and I want to give you one more example. So I'm going to open now another image because it may be that you have collected label data in a field with GPS, which is more accurate, obviously, than doing it manually. So if I enter an image, right, and then this image should appear. So let me delete all this data. So this is a region in Iran. Also, I forgot to tell, because we have another option, is band stacking. And band stacking is in case your image consists of individual bands, as is often the case for Sentinel-2. You can stack them yourself. So let me quickly show you. Let me go to the individual bands. So here we have these Sentinel-2 bands. You just select them all, and they will appear. Normally they order themselves based on the name that is being given, but you can swap, so you can reorder them. And let me add all these bands. I'm fine with it. And now if I would click on done and export, it will created a stacking, so it would make one single image, a data cube, which we use for these LabelMeClass tools. So I will not do so because it may take some time. It's just for you that you are familiar with. And the final result is this image. Let me also show it as an RGB. Okay. And in this case, so I can do again, select my pixels, but I have a file available with GPS coordinates. And let me select that one. I believe it's here. And maybe one up. Right, so here it is. And so we can see, so we have X and Y coordinates, and then the labels has been collected in the field. I see it has a header line, so I will remove that one. I click on OK. Now MATLAB checks if it can read it. And now what we have to do is to say, okay, column 1 is the longitude. So I set that. Column 2 is the latitude, right? So that's the Y. And then finally, column 3 are the labeled data. Okay, we can have a look at it. That seems fine. And then finally, we can import it. And now it will identify if it's within the image. And I see an error appeared because probably I was a bit too fast. So let me quickly close this and repeat it. It was working before, so I'm sure it will work. So let's quickly open, get our image. And then finally load the coordinates. Right, it was here, okay. And let's hope this time it will work. Okay, so set latitude. And then finally the labeled data. Right. So we can see this was the first class, the second class, and the third and the fourth. And we can see the colors appear. So you can see where these classes, where the data has been collected. And this looks like a perfect data set. Here in this case, because we didn't give a name ourselves, so we can edit the name. So this would be plant ecological unit 1, and so on and so on. And then you can apply it. And then even you export it, it also is being exported to the meta file of the text file of the data. So that was for the label me. Now let's go finally into the classification toolbox. So I close this. Maybe let me clean up a little bit. And let's go to the classification toolbox. Just as any other of our toolboxes, we always start with data. So we don't start with an image. We first start with data that we use then for training or parameterizing and validation. If you are happy with the validation, with the results, only then we apply it to an image. So the first step we have to do is select our data set. And so I can click on browser and select text file. So in case of Valencia, I think it's this guy here. And yes, so this is our labeled data that I had prepared before. And I have to say then a given name. So let's say Valencia classes, let's see, and is line number 1. And then you extract it. In this way, it also means that I should, maybe I want to change the colors to make it sense. It's only the problem is that now I don't know what is the meaning of these classes. So we could assume class 1 is C. So for this reason, it's good to have your meta file available and then give appropriate color. I will now do a shortcut because I had it also prepared. So apart from browser and selecting your text file, once you have it prepared one time, you can always save these settings and load afterwards. So I'm going to load on what I had prepared before. It's this guy here. So here I have the proper colors and labels already, or names prepared. Okay, exactly. So we see we have buildings, and it's in, I think if I click on it, I see in which color that is being provided. So in this case, building is white. The park is in, sorry, I have to do it differently. I have to click here, right? So you see the color below: buildings, park in green, industrial buildings also white, apparently, lake in blue, rice fields in dark green, roads, and so on. So if I'm happy with this, and it seems like also I can plot the spectra. So this is the collection of the Sentinel-2 data. This seems to be fine. It looks very messy, but we have many classes, so it can make sense. So we just click on import. We don't need to add the spectral units. I know it. I don't have provided the wavelengths, but also the image does not have the wavelengths, so it's fine. And finally, we have loaded the data, and we can go to the most important step, to settings. So in settings, here we have all the algorithms. We have 22, and you can just select any one that you like. So you can select all of them if you wish, but also you can select them according to their nature. So we have the parametric algorithms, the decision trees, this is a MATLAB kind of ensemble way, error correcting output codes. And within this way, you have the support vector machine, decision trees, key nearest labor, and so on. Basically, these are assembles of these methods. We have ensemble learners. We have all kinds of neural networks. And finally, we have discussion processes. And let's show all. And because this Valencia dataset is a bit large, I will just run now the maximum likelihoods. Later with the Iran dataset, we can do all of them. It's just to be a bit fast now. So we need to say how much of the data we use for the training, and the remaining data is then for the validation, for calculating the accuracies. In case we have hyperspectral data, we could apply dimensionality reduction so that we can combine our data with, for instance, principal component analysis, but we have more dimensionality reduction methods. So basically, you just say, first convert my data according to PCA for so many number of components, 5 for instance, before applying the classification algorithm. I will not do so now because Sentinel-2 with 10 bands, that should be enough. And so let's click on, oh yes, and then we have also data tools, cross-validation options, and for external validation data here, because it could be that you have your training data in one file and your validation data you collect elsewhere or on a different time or so on. So you could load that file here in validation data. So exactly the same window will appear, meaning then that you have your training data and your validation data separated. And then there are these advanced options, depending on the algorithms that you have selected, you can tune it, right? You have all kinds of options to further improve that algorithm. For instance, discriminant analysis often perhaps works better when it's a quadratic function. Anyway, I keep it how it is for now. And so that was just simple, but in case you have more advanced algorithms such as neural networks, you will see more options will appear on tuning it. Fine, so let's move on and let's select this, and we just give it a name. Automatically, it will suggest the name. So this is the name of the file, of the training file. It used the discriminant analysis, but you can change it. So for now, I just keep it. And now it will start evaluating this single algorithm. It's a very simple one, so it's supposed to be very fast. Here it is. And we have this overview of the overall accuracy. We have kappa, the total time of running it, training time and testing time. Then when we click on plot, we have the confusion matrix that should appear. And let me make this a little bit larger so that more information appears. So we see the confusion, so how and where the pixels were assigned to correctly or to other classes. And then we have some statistics also for, these are the total statistics. So we can see where, and normalized in percentage, where the pixels were assigned to. There are some options also to change this that you show instead of, here we show the total statistics. You can also show the statistics per column or per row. these options later I can show where to change it, but this is just the default setting. And then also we have the statistics per class. Let me make this a bit larger. So we have the, okay, the precision, sensitivity, specificity, and the F1 score. So we can see which classes are very well. Obviously, C, which was a very easy class, and what else? Apparently, the open mine pits, which is also very widely shown. These were easy classes, and the lake and other classes are much poorer identified with park, because park here resembles very much to natural vegetation, for instance. So we have this overview, and I think we also have the information of the training data, although always the validation data is what matters, no? But I believe we can show also the confusion matrix for the training data, which typically looks better than the validation. Okay. Finally, if you are happy with this method, we can apply it for mapping applications. So you select it, and we can click on done. And then we can go to the next step to image. In this case, we can write, when we classify, you can classify either an image, which is most of interest, but also it could be that you just have with spectrometer collected spectral data, and you want to classify that in whatever classes. So you can also select a text file, which just consists of spectral data, and it will apply these algorithms, and then it gives you a text file as output with the classes, so with labeled data. So in case of image, we have selected this discriminant analysis. In case that we do not want to do validation, we could also here click on new model, select directly an algorithm, and we skip the validation step, but that is not recommended, because it's always good that you know something about the accuracy of your model. So first do the validation, then apply it to classification. Okay, so we can select this, and we then select an image. In this case, it's the Sentinel-2 image. And then it will suggest us an output. So basically, it just gives the classifier at the end, and finally it will run it. In this way, we have our map. This should go pretty fast because it's a simple classifier. If I would apply more complex ones, such as these Gaussian processes, it would take too much time. That's why I will not show it now with this data set, but here afterwards, I want to show the smaller Iran data set, and then we can also see the performance of these Gaussian processes and plus the uncertainties. Okay, so now our map should appear. Yes, so here we have our final map. This window appears that it always appears. Sometimes maybe there are more bands, not here in the case of classification, but also you can open other outputs. So with I also did it, for instance, with another algorithm, and so we can compare these different. Here is the other one. Probably it's pretty much the same. So this is with also maximum likelihood, but this ACOG, so this assemble of maximum likelihood, while this is just simple maximum likelihood. And yes, and one more thing also, I believe if you are not happy with the colors that you have provided, it's still possible to change the colors. Yes, so here this small window will appear, and yes, you can change the name, right? And you can change the colors also. So you have some standard colors, but you could also well, give your RGB numbers, or so that you have that option available. Okay. So this was the, let's say, the basics. Now let's try to do some a bit more advanced options that are also within the toolbox. I will close this. Let's close this out. Let's start again. Classification, supervised, input user data. And now I will load directly. So I can go to browser, but I think I've done it already. So I can directly load Right, this guy here, this has just 4 classes and with what has been collected with LabelMeClass. These are 4 plant ecological units, so just vegetation types. And yes, so you can see it from LabelMe because we have this geo information, pixel number, the labels, and then in this case, it has only 6 bands. Right, so we import it. And now let's just select all the algorithms so we can see which one is doing well, which not. And yeah, so there's no need to do dimensionality reduction because it has only 6 bands. Also, I could apply for cross-validation, so meaning that you don't do a simple split training testing, but basically you use all your data for training and all for validation. And now the advanced option, you can see all the algorithms are available for changing options. So for instance, if neural networks, you can change all kind of optimizations. And also there is this info button that will guide you to the MATLAB page to give you information what all these options mean. So that you are not kept in the blind. So let's again select 70% for training. The remaining is used for the validation. And let's run it again. In this case, I say all classifiers. Okay, this will take a little time because now we evaluate 20 different algorithms. Yet I believe we go pretty fast. We see in MATLAB what has been done, and we see also the time bar. Now some more windows will appear because we are also running some neural networks, and these more advanced algorithms, they try all kind of designs of neural networks, so initiations, a number of neurons, which makes it takes a bit more time. And also, I believe some windows will appear where you will see iterations of further optimizations. I'm not sure if here Miguel is here, probably not, or Jose Luis. They can explain you more about how this works as these guys have developed it. So this is the neural network, and right, so you can see that it starts optimization. So it's iterating each time with different settings for finding the optimal neural network design. And we have to go through thousands iterations, so it takes a bit of time. But then the funny thing is that often, even though it does all these optimizations, often it's not the best performing algorithm. So that's why I would say it's always good to try different algorithms, because depending on your data set, one algorithm may work better than another. And you can only know well if your algorithm is the best one if you compare it against the others, right? So I would say just try all of them and let's see what comes out. So this is done, the neural networks. I think I can minimize it. And yes, we just have a few more to go. And then finally, again, the overview window will appear. And in this, so we can see that in this case, one of these neural networks is best performing. Let's make it a bit bigger. So this is neural networks. But if we go down, there may be other neural networks that are not performing so well. I'm not seeing them right now. Okay, so we have the neural network, the ensemble, linear classification, and so on and so on. Results are pretty good, I would say so. But let's have a look to some specificities. Well, first we can see the confusion matrix again. In this case, we have only 4 classes and not too much data. So that's why it went so fast. But I want to show you now something extra in case of these Gaussian processes. In this case, it's just averaging performing for this data. Because now a new option here appears, which is the sigma bands, either as bars or maybe more interesting as polar plots. Because these polar plots, they give you information of the relevance of these bands that I had available. These are 6 Sentinel-2 bands for each of these classes, right? So, and the further away, the more important. So we can see that plant ecological unit 4 especially made use of band number 3. So we have this little extra information. Let me use now this discussion processes for mapping, because then we can see the other interesting feature. So again, I go to classification, image. It's selected. All we have to do is select our image. I need to make sure that I'm in the correct folder that the bands match. I believe it's this guy here. And we give an output. Also, I need to make sure I'm in the correct folder. And then let's run it. Yeah, because it's pretty small image, it goes quite fast. But when the image is big, like Sentinel-2, it can take really long time. Here also, I would when you try algorithms and mapping, I would recommend first try on a small image always, so that you have some feeling if it really makes sense before you process a complete image. And also the way it's designed, it processes per blocks. So it's never loading a complete Sentinel-2 image with several gigabytes. It's always taking just a piece of it, process it, write it away. And in this way, it allows to avoid memory problems. And you can, in options within the toolbox, you can define the size of this block. So in case your computer is very powerful or your image is small, you could decide to make these blocks larger. So here we are, we have this map of the plant ecological units. And now of interest is that we can open, because a new also output appeared. So the same name, but with added standard deviation, so which is function as the uncertainty around the, well, in this case, it's not estimated, it's labeled, it's classified, but it provides the uncertainty as a standard deviation, which is this map. So we can see our output map, and we can see where the classifier did a great job. So with the lower uncertainty and the lower standard deviation, and where it did a poor job. So the yellow areas there, it was not so sure. And with this, I think we covered most of the topics. I just want to show you also this in tools, basically, where we have this view map, view figure. You can export from elsewhere, import it here. You can also apply your algorithm to additional new validation data here. So once your model has already been developed, you can validate new data here. But maybe most of interest are these options. And in options, you can define the size of these blocks, as I said before. You can activate or deactivate some processing options. Also here, like with this confusion matrix, what I said before, you can change what you want to, show. And so it was showed as total normalized on columns and row, but you could change these what you would like to show as additional statistics. And right, and then finally, maybe also of interest, so we can always go back to our results. So if I click on load, these are the ones that we just did. We have this meta information, so the part of your original data, number of samples, number of wavelengths, the band names, the classes names, and yeah, the name that you gave to your classes. And so this can be also another one. So you can always go back and load your results again. So nothing is ever lost. All this data is all stored within MySQL, which is running underneath. But maybe also it would be good every now and then that you remove results that you no longer need. And this you do here in Tools, Manage Test, Rename or Delete. And then you can just select any of them. And this way, these results are deleted. And with this, I think I close my tutorial. We have covered everything. So there's still 10 minutes maybe for questions. Thanks a lot.